Okay. So, thank you, Hoa, for accepting the invitation. And today she's going to talk about the homological properties of braided Hopf algebras. So, thanks again, and you can start when you feel ready.
Yeah, thank you very much. And also thanks to Neishi because we haven't met in China. So he's
Okay.
proposed me to give a presentation. I'm so happy to be here today. So, okay, as you said, I will present a little bit about homological property of braided Hopf algebra. This is a work for the first article with my supervisor. So, to explain the motivation of our work, oh wait, okay. So I will firstly explain our motivation and then the first part of the presentation about the cohomological dimension of braided Hopf algebras. And then the second part will be about twisted Calabi algebras. So uh, before I start, let's recall some definition of cohomological dimension. Uh, let A be an algebra and let M be a left A module. And the projective dimension of the A module M is the smallest possible length of projective resolution of M. And then it can be characterized as the supremum of a natural set, as I write here, such that we have an A left A module and with the X space of n with coefficient in n is different 0. And then we have the Hochschild cohomological dimension of A is the projective dimension of A as an A bimodule. And we also have the definition of left global dimension of A. It's just the supremum of projective dimensions of every A left module. And similarly, we also have the definition of right global dimension. And when these two agree, we just say global dimension. And there's a well-known fact is that we always have the global dimension of A is smaller than or equal the cohomological dimension of A. Okay? And we know that the global dimension is an important homological invariant of an algebra, but there's some example, it doesn't match with geometric iteration. For example, we can see if we take K be a field and we look at the first Y algebra denoted by A1, we know that, well, this is a different, how to say that, the deformation of a polynomial of two variables. So morally, it should have a dimension 2. But if K has characteristic 0, we know that the global dimension of A1 is 1, proved by Reinhardt in 1962. And however, we also have the cohomological dimension of A1 is 2, and it coincides with what we expect. So for us, it's better to consider the cohomological dimension instead. And our question is that when do we have the cohomological dimension and global dimension coincide? And until now, we know that this is true if we have A is a graded connected algebra. And the second case is if we have A is a Hopf algebra. So we would like to generalize the case of Hopf algebra to braided Hopf algebra. So the objective is that we want to prove the following theorem. If we have A be a Hopf algebra in braided category denoted by MH of comodule over coquasitriangular and cosemisimplecity Hopf algebra H, then we have the cohomological dimension of A equal to global dimension of A left and right, and also equal to the projective dimension of trivial left or right module. So the first part of my talk, I will try to prove this theorem. So before we go into the proof, I will recall some concept of braided category and Hopf algebra within braided category. And then
Sorry, one question here.
yeah.
The the coquasitriangular and cosemisimple Hopf algebra, and so the H and the A, they are both algebras over the field K, right?
Yeah.
Okay.
That, like we have a H is a Hopf algebra, but over K, but there's some structure that I will recall after if you want. I will put it in the slides. You will see the definition more in detail.
Okay. Okay, thank you.
Yeah, okay. So firstly, we have the braided category is a monoidal category C endowed with a braiding. It means a natural family of isomorphism denoted by CXY that we change X tensor Y to Y tensor X, such that we have some specific diagram commutative. And then we have we always use some diagrammatic notation as for the identity morphism or morphism F in the category C, or the braiding C and its inverse, as I write in the slide. And then the simplest example of braided category is the category of K-vector space with the braiding given by flip operators. And the second example that we want to is the category that we want to work with, as you ask as questions. So first recall, a coquasitriangular Hopf algebra is a Hopf algebra H endowed with a convolution invertible linear form R, such that we have some specific relation. And then when given a linear form R, we know that the category of H comodule MH is braided with the braiding given by this formula that we just use we compute the H coefficient of V tensor W, and then we apply the R form to the V1, W1, which are in H, and we treat V0 and W0. This is a formula for our braiding. And in this case, we can look at a concrete example. For example, if we have H is a group algebra, so let gamma be an abelian group, then the universal R form of the group algebra K gamma, we know that K gamma is Hopf algebra. And moreover, is also is a coquasitriangular Hopf algebra with the bicharacter, with the braiding correspond to the bicharacter of gamma. It means that we have the map psi such that we have the following relations. And then there's well-known fact is that we know the category of K gamma comodule identifies with the category of gamma graded vector space. So thanks to this fact, and given a bicharacter over gamma, we know that braided category M K gamma, we know that the category of a K gamma comodule is braided, and with the braiding given exactly at the above case. Okay. So, as in an ordinary case, we also have a definition of algebra and co-algebra in a monoidal category. For example, if we have a C be a monoidal category, an algebra A, an algebra EC is an object A of C, endowed with the morphism M that we call the multiplication or product, and the unit eta, such that we have exactly the same relation in the ordinary case. And similarly, we also have the definition of coalgebra in C, as in the classical case. And we usually use some dramatic notation for the multiplication, the unit, co-multiplication, and co-unit. But there's one thing is that there's no natural way to formulate a definition of Hopf algebra in a monoidal category, because normally we ask that for example, the morphism multiplication is an algebra morphism. But in this case, it's just in a normal monoidal category, we cannot have the algebra structure on the tensor product, this C tensor C. But it becomes possible if we work in the braided category, thanks to the following construction that I detail here. Let's C be a braided category, and let A and B two algebra in C. The braiding C gives us an algebra structure on an object A tensor B with a multiplication given by our morphism M here. Specifically, we just need to use the braiding to treat B and A in the middle, and then we use the multiplication of A and B to both sides. And then these guys give us a multiplication on A tensor B, and then we obtain an algebra denoted by A tensor with a small c here, A tensor B, and we call that this one is braided tensor product algebra of A and B. And then thanks to this construction, we have the definition of a B algebra in C. We see a braided category, an algebra structure and co-algebra structure. And we ask that the co-product and co-unit are algebra morphisms, and the properties is given in detail here. And then also, because we have a definition of B algebra, we also have the definition of braided Hopf algebra. When we ask if we have a morphism called antipode and satisfying exactly the same condition in the classical case. Okay. Okay, so an example of braided Hopf algebra, I will talk a little bit about the two-parameter braided quantum SL2. And the definition of this object, if we take P and Q in K star, and the algebra OPQ is the algebra presented by generator ABCD with some specific relations. Here, if we remark that if we take P equals Q, we have exactly the same definition of OPQ SL2 in the classical case, the quantum proof in the case of K vector space. And then we show that the algebra OPQ have a KZ comodule algebra structure with the cohesion defined by this algebra map, where the small z we have here is just the fixed generator of the infinite cyclic group Z. Okay. So because as earlier we have seen that KZ is a braided category, and if we consider the bicharacter C here, uniquely determined by psi ZZ equal pi P minus 1Q, and as we have seen that MKZ is braided category, and then we show that actually our OPQ that I denote by A is a Hopf algebra in the braided category MKZ with the co-multiplication, co-unit, exactly the same in the classical case, it's just our antipode is a little bit different. But if we take P equals Q, it becomes the same in the classical case. Okay. Okay, so this is an example of braided Hopf algebra in the category of KZ comodule. Now we will come back to the proof of our theorem. So the first thing we need to do is that we will construct some module and bimodule over a braided Hopf algebra. So let C be a braided category and let A be a bialgebra in C. Let V be a left A model in the category C. Endowed V tensor A with the right A model structure defined by the right multiplication on A. And then we have the following morphism, mu. This one provides V tensor A with a left A model structure, and then with an A bimodal structure on V tensor A. Well, specifically for mu, we just need to we need to compute the coproduct on A, and then we use the braiding to treat the second copy of A with V, and then we apply the left A model on V and the multiplication on A to both sides, and then we obtain the left A model on V tensor A. And we have the new bimodal denoted by V box term A. So this construction gives us a functor denoted by L from the category of A module to the category of A bimodal. And we can do the same way to construct another functor which works in the opposite way. It means from the category of A bimodal to the category of left A model. That I think, yeah, this one. If we have a C, a braided category, and left, and A be a Hopf algebra in C, let M be an A bimodal in C, and then we have this morphism mu that we first use the co-product on A, and then we apply the antipode on the second copy of A, and we treat this one with M by using the braiding, and then we use the bimodal structure on M, and we obtain this morphism, and this one endows M with the left A model structure on C in C. And then we denote by M tilde the new A module. And as I said, this construction gives us a functor from the category of A bimodal to the category of A module. Okay, and then with the two functor, we then show that actually the functor R is right actually to the functor L. And then it follows us to use a classical result is that if we have a K and D be K-linear abelian categories, and let F and G be some two functor between the two categories with the condition that G is right actually to F. And moreover, if we suppose that C has enough projective and exact, then we have a natural isomorphism between the X space over D of Fx with coefficient in V and X space over C of X with coefficient in G of V for any object X and X in C and V in D. So with two propositions in hand, we now just apply like G by R and F by L. We obtain the following result is that if we have C be an abelian K-linear braided category with enough projective, and let A be a Hopf algebra in C, and we know that there exists a natural isomorphism between the category of A bimodal, the X space over the category of A bimodal of A with coefficient in M, and the X space of over the category of A modules of the trivial A model with coefficient in M tilde. And thanks to this isomorphism, we have the projective dimension of A as an A bimodal equal to projective dimension of trivial left or right model. So the proof of this corollary is not really difficult because, as I explained, because we use the two projection here by replacing F by L and G by R. And then we have the eighth space of E both time A. This is L, our functor L, with coefficient in M and is isomorphic with the eighth space of trivial A model with coefficient in M tilde. And here we remark that because we have this isomorphism, because we have on the hypothesis as we need, with the fact that our category is K-linear braided category, so the functor, the tensor functor is supposed to be exact and K-linear. That's why we also have the category of A bimodal, and A model are also abelian K-linear. Because it's not really the case when we have a C is a monoidal category, is not really always the case that the category of A model or by A bimodal is also monoidal. That's why we have the assumption on the tensor functor. Okay, so thanks to this isomorphism, we have the projective dimension of A as an A bimodal is less than or equal to projective dimension of the A trivial model. And then if we take M is a model in the category of C, and if we use the co-unit, we can have M as an A bimodal, and then we obtain another term, our functor R, and that's why we obtain the M var epsilon tilde is an object in the category of A bimodal. And then by using this isomorphism, we obtain the X space of the trivial A model with coefficient in M is isomorphic to the X space of the trivial model with coefficient in M var epsilon tilde. And then by using another term, this above isomorphism, we obtain the last isomorphism here, which is the X space of the trivial A model with coefficient in tilde M var epsilon, and the X space of A with coefficient in M var epsilon. And by using this isomorphism, we obtain that the cohomological dimension, the projective dimension of the trivial module now is less than or equal to the projective dimension of A. So by combining these two inequality, we obtain the equality as we ask in the corollary. Okay? So now, if we take C is the braided category that we want to work with, is the MH. Always with H is a coquasitriangular Hopf algebra. Since we have this equality just have seen above, the first thing we have is that the global dimension of A is always smaller or equal to the cohomological dimension of A. And this one, by definition, is the projective dimension of A as an A bimodal. And this, the last projective dimension is smaller than or equal to projective dimension of A as an A bimodal, but in the category MH. And by using the equality here, we have the last projective dimension equal to the projective dimension of K as an of the trivial A model in over MH. And our question now is that whether we have the projective dimension of K as an A model over MH equal to the projective dimension of A of K as an A model in the category in the classical case. Because if we have this equality, and we know that the last one is smaller than or equal to the global dimension of A, and if this equality holds, we have one of these projective dimensions coincide. So to answer these questions, we then need to work with another tool. It's called the separable functor. That here I recall the definition. If we have C and D be category and let F be a functor between the two categories, and then we know that F gives a natural transformation denoted by P between the home space over C and home space over D. Then we say that F is a separable functor if there exists a natural transformation which works in the opposite ways from the home space over D to home space over C, and such that we have composition of P with M equal identity. And then we have a proof that if we have C and D be Euclidean or abelian categories with enough projective object, and let F be a functor between the two categories, suppose that F is exact, preserve projective object, and also separable. We show that for any object X in C, we have a projective dimension of X over C equal to projective dimension of F of X. An example of separable functor, we use the following result. Let H be a cosemisimpple Hopf algebra. And now we remember why we have the cosemisimpple in our theorem. And let A be a right H comodule algebra. Then the forgetful functor from the category of A model over MH to the category of A model are separable. This just one word for the last proposition. This one have proved by various authors in different way, but we then saw that we can do it directly by using the house integral in given that H is cosemisimpple Hopf algebra. And then now we just need to use the two propositions, and then we obtain the last this equality between the projective dimension that we want to do at the beginning. And now we have one of these projective dimension coincide, and we obtain the following theorem that I want to show. Let A be a Hopf algebra in braided category MH of comodule over a coquasitriangular and cosemisimpple Hopf algebra. Then we have the cohomological dimension of A equal to global dimension of A, and also equal to the projective dimension of the trivial model. Just one word for this theorem. For us, it's interesting to have this result because sometimes when we want to compute the cohomological dimension of an algebra, thanks to this theorem, it will be easily to work with the trivial A model than we compute directly with A as an A bimodal. To prove that what I said, I will give an example to see how we can use our theorem to compute the cohomological dimension of the Hopf algebra OPQ that we have seen earlier. So the first thing we need to do is that we have to find a resolution of K by A modules. So we have found this resolution. This one actually, if we have a P equals Q, this is a resolution of Kramer. It's having in 2005, and we just changed a little bit to be work in our situation. And thanks to this resolution, we have the projective dimension of trivial A model is less than or equal to 3. So, and then the next step we need to do is compute the the active space to have the equality. And then, so if we take T non-zero, we know that there exists an algebra map via epsilon T here. If T equal 1, it's just the co-unit of our Hopf algebra, OPQ. And then if we put T is a PQ minus 1, by using some computations, we found that the X space a degree 3 of K with coefficient in K, but depends on var epsilon T is isomorphic to K. So it's different to 0. So by definition, we have the projective dimension of K is greater or equal to 3. So we have is smaller and greater 3. So we have the cohomological dimension of OPQ is 3 by using our theorem. Okay. I don't know if you guys have any questions before, because for the next part, we can also show that actually our OPQ we treated Calabi our algebras. So if you don't have any questions, just until now, I can continue. So for the next part is about treated Calabi our algebra. So firstly, I will recall the definition of treated Calabi algebra. So let A be a K algebra, and A is said to be smooth if A is of type FP as an A bimodal. It means that A has a finite resolution by finitely generated projective AE models, or A bimodal is the same. And we also, so A is said to be treated Calabi of dimension n if A is smooth. And we have the Hochschild cohomology of A with coefficient in A tensor A. It's isomorphic to 0 everywhere except n where is isomorphic to A as an A bimodal, but treated by the Nakayama automorphism mu. Okay, and then the motivation for behind the treated Calabi algebras come from the following result of Van den Berg. He said that if A is treated Calabi algebra of dimension n with the Nakayama automorphism mu, then we have the cohomological dimension of A equal n, and if M is an A bimodal, then we have the Hochschild cohomology of A with coefficient in M and the Hochschild homology of A with coefficient in M mu minus 1 are due one to another. So this is the motivation of treated Calabi algebra. So this one is a little bit tricky because we want to generalize, give some example of treated Calabi algebra, but in the setting of braided Hopf algebra. So this one is generalized result of Brown and Young in 2008 for ordinary Hopf algebras. So for this part, I want to try to prove this theorem that if we let A be a Hopf algebra with bijective antipode in the braided category MH, always, with H is a coquasitriangular Hopf algebra. Suppose that the A model K, the trivial A model, is of type FP in the category of A model over MH. Then, and also suppose that there exists a natural number n such that the X space vanish everywhere except n where it's one-dimensional. Then A is treated Calabi of dimension n with nikaimorphism defined by this following formula. For now, we don't need to go in the detail of this formula because we will see it later, a bit later in the proof. But so firstly, I think we need to understand what does this mean. A model is of type FE in the category of A model of MH. And then we will show that under the assumption we have A is smooth because smoothness is the first condition to be treated Calabi algebra. And then the last one we have to do is to compute the Hochschild cohomology. So let's go with this first thing for the finiteness conditions. Let's see be an algebra, let's see be an abelian K-linear monoidal category. And it always means that our tensor functor is exact. And let A be an algebra in C. An object V in C is said to have a left dual if there exists an object V star together with satisfying the two specific conditions involving the evaluation morphism and co-evaluation morphism. And then we say that a left A model M is finite relative projective if M is isomorphic, and then as an A model to the direct summand of three A model A tensor V, with V is an object of C having a left dual by the above definition. And then a left A model of M in C is said to be of type FP if it has a finite resolution by finite relative projective, which means that we have an exact sequence of A model at this one, and each term in our resolution is relative projective. Okay, so now as I said, we want to prove firstly that A is smooth. So we remain the construction of the first part that I found L here. If you remember, let C be a braided category, and let A be algebra in C, and let V be a left A model in C, and we have V tensor A is an A bimodal, and we have a scene. And we denote by L the functor from the category of A model to the category of A bimodal. And by using this functor, we know that this one transforms three A model into three A bimodals. And if moreover C is an abelian K-linear braided category, then the functor L transforms objects that are of type FP in the category of A model into objects that are of type FP in the category of A bimodals. For the proof of this proposition is not really difficult because if we take A tensor V, a free object in the category of A models, and we apply our frontal arrow. We have this one, and we just need to prove that A tensor V per time A is isomorphic to A tensor V tensor A as an A bimodal. So we have a free object in the category of A bimodal. And because we have the tensor frontal is always exact, so it's preserved resolution. So we obtain what we want to have in the proposition. And then by using this fact, we have the following theorem. Let A be a Hopf algebra in the braided category MH. As always, with H is coquasitriangular Hopf algebra. And if the trivial A model is of type FP over MH, then we have A smooth algebra because we just need to take C is a MH, the category that we always want to work with. And we have a arrow of K epsilon is isomorphic to A. And then by using the above proposition, we know that A is type FP in the category A bimodal over MH. And also that is of type FP in the category of A bimodal. So we have A smooth as algebra. So this one is we finish the first step to prove treated Calabi algebra. And the last thing we need to do is to compute the Hochschild cohomology. So before I go into detail, we will fix some Swiss notation. We denote by because we have a Hopf algebra H, but we also have the Hopf algebra A in the category MH. So we use the square brackets to denote the commultiplication of A, and the brackets to denote the commultiplication of H and also the H coefficient on A. Okay, so with the three notations, we have the following theorem. Let A be the category MH as a way. If the trivial A model is type FP in the category of A model over MH, then we have an isomorphism of right A models or A bimodals between the Hochschild cohomology of A with coefficient in A tensor A and the X space of K with coefficient in A tensor A. Because this one is an isomorphism of right A models, so we need to give the structure on the two objects. So where we have the right A action on this guy, the tensor product of X space and A defined by this very tricky formula. But I don't think that we need to go into detail, but we know that the right A structure on the X space is just induced by the right multiplication in A. And the right H coefficient is given by this morphism. But to understand this morphism, we need to see the next proposition that we have constructed.
Excuse me, Hoa.
Yes, tell me.
In this, I mean, everywhere when you have a
Yeah,
tensor product, is the tensor product of modules, or like using the commultiplication?
yeah.
Okay.
This is the tensor in the classical case. But no, but the thing is that we will see that our X space is also an object in the category, in the braided category.
Yes.
And A, for now, it's just the tensor in the case of vector space. But then we have to see, we will see that this one is also an object in MH, in the category of H comodule. And A is also an object in the category H comodule. So the tensor product, we have to pay attention with the braiding.
Why is the X inside the X is okay, the action that you are
We will
defining
see
there.
now.
Okay,
Right
okay.
now, we will see. Yeah, but good question.
Okay.
Thank you.
Thank you.
Yeah, because we have the right, we have the,
Yes.
yeah, for example, I will show the two lemma, because the idea is that we will
Previous
take a
slide,
resolution.
perhaps. Previous slide, perhaps. You have the previous slide. The previous slide
Yes,
is
this one.
the structure of Hochschild cohomology as I bimodule is what?
Sorry, the structure on Hochschild cohomology as
Yes.
an AE model, right? Is that your question? It's just the multiplication on the right of the tensor product.
Inside the tensor product.
Yeah, because we have the multiplication on the right, and then we do some, we can do, how to say that? Because firstly, we will we define the AE action on the A tensor A, and by passing to quotient, we can obtain the right AE action on this one. But this one is a symbol, it's just the multiplication on the right. But this one is more complicated.
Know if this theorem is false without the hypothesis of K being FP,
Yeah, K is of type FP.
but you know this theorem is false without the hypothesis.
Yeah. We need to have
No,
this hypothesis.
because you know a counterexample.
For a counterexample, I don't have any in my head. Actually, I was thinking about it, but I didn't find any counterexample. But when we do work, I know that I have to put it inside to work my theorem.
The proof needs that hypothesis, I believe, but I will be happy to know a counterexample.
Yeah, that's a good thing. I think I have to think about it after, but actually I will think about it, but I didn't find anything until now for a counterexample. But if you have any idea or any help, I will be so happy to talk about it.
Okay, thank you.
Okay. Do you have any question so far from this theorem? Okay. Okay, so let's go back to the proof of this theorem. Because I said that we have an AE action on this guy, the tensor product of H space with A. And we have also H comodule structure on the H space. And this one is just, we have a resolution, and we apply our Fountain Home. And the idea that we will divide our Fountain Home as an H comodule, and then by passing to quotient, we can obtain the H coaction on our object. So the first work that I did is that if I take P is a finite relative projective object in the category of a model over MH, then we have this morphism defined by this definition. And I know that this one in doubt home a P with coefficient in A, an H comodule structure, and then this one is an object in the category of write a model over MH. And then by passing to quotient, I obtain the object H space is in the category of write a model over MH. So that's one we have. This one is an object in the category A model. So now we are ready to prove our main theorem. Let A be a Hopf algebra with bijective antipode in the braided category MH. Suppose that our trivial A model is subtype FP in the category of A model over MH, and that there exists a natural number such that the H space is vanished everywhere except N, where is one-dimensional. Then A is treated Calabi of dimension N with the Nyquist automorphism defined by this following formula. And here we have the C appear in our formula because it's just the algebra map corresponding to the A model structure on the H space that we have seen earlier, and satisfying this condition because we have the compatibility, I don't know how to say that, the compatible condition between the H comodule and the H comodule and A model structure. And then the G here, it's just the group-like element correspond to the H comodule structure on our H space. To the proof, we will see now, because we have seen earlier that we have the isomorphism between the Hochschild cohomology of A with coefficient in A tensor A and the H space of K with coefficient in A tensor A. If we suppose that the H space is 0, and then it's clear that we have the Hochschild cohomology is also 0 for any small e different n. And moreover, if we have X is one-dimensional, then the H comodule structure on X space corresponds to the group-like element G. That's why we have the small g in our formula. And I said the C is just the A model structure on the X space. And because we have the X space is an object in the category of A model over MH, then we have the compatible conditions. And then by doing some computation, we found that the AE action on X space tensor A is this one. And if we look at the right-hand side, we obtain the formula for our mu. Okay. And then we will see how to use our theorem to prove that our OPQ is also treated Calabi algebra of dimension 3. And so the first thing I put here is the definition of OPQ in the case if we forgot. So is the algebra represented by generator ABCD with the specific relations. And we recall that MKZ is an abelian K-linear braided category. So as usual, the first thing we need to do is to find a resolution of K, but in the category MKZ. So we found this resolution, and if you remember, it's similarly the resolution that we have found in the first part, but we changed a little bit to be a resolution in the category MKZ. And by using this, with this resolution in hand, we know that OPQ is smooth. And then the last thing to do is to compute the Hochschild cohomology. So on way will remain our morphism, algebra morphism by epsilon t, and with t equal 1, it shows the counit. For t is p q minus 1, we found that the X space of K with coefficient in A is 0 if n is different 3. And if n equal 3, we have a X space at degree 3 is isomorphic to K, but depends on var epsilon t. And so it's one-dimensional. So by using our theorem, we found that OPQ is treated Calabi out of dimension 3 with Nekayama automorphism defined by this formula. And I also, I think it's, yeah, that's on what I want to say. For the formula of mu is not difficult, it's just using the formula in our theorem. And so I think I finished my presentation here. And thank you very much for attention.
Thank you, Hoa. Very interesting.
Thank you.
Thank you very much.
Do we have any questions for Hoa?
It seems to me that
Yes.
Apple proved the cohomological dimension of A equals the projective dimension for finite dimensional algebras. The equality you say at the beginning it's proved by Apple 20 years ago for finite dimensional algebras, parce que there exists a finite resolution by using Tor between simple modules, a finite projective resolution minimal using the Tor between the simples for finite dimensional algebras. The equality is proved at the beginning.
So you mean that the theorem at the beginning
The theorem is
between
proved,
the cohomological dimension of A
yes.
and the braided and the projective dimension of trivial mode K is true?
The dimension of A as a supremum of the projective dimensions of left modules is proved for finite dimensional
For finite
algebras
dimensional, yes.
over a field.
Yeah.
Yes. You agree, Andrea?
Yes. But nothing to do with Hopf structure.
Yeah.
Yeah.
Yes.
But for finite dimension, I agree that is true. But as algebra, she said that we have nothing to do with without this condition.
No, I mean that it is a result for algebras, just finite dimensional algebras, independently of the fact of having a structure of Hopf algebra.
Associative algebras.
Yes.
So here the global dimension, if I understand correctly, is calculated in a different category, right? I mean, the category of comodules instead of the modules, or?
Sorry?
Let us go. Maybe we can
Yeah,
go
maybe we
back.
can see the first
Yeah,
first
at the beginning
theorem.
of the.
For the first, maybe no. I will go back at the beginning.
Mhm.
Yeah.
This one?
No, the first one slide. This is the first.
So this one.
The first one.
The
Let's go
first
back
one
to
it
the
shows
first slide.
the first line is this one. So
No.
I don't.
The
So
third,
the first theorem that you want to see, or the first slide?
no, the third slide.
The third one.
The
Here. Okay.
yeah.
Here we are talking about algebras. Okay, so
Mm.
when we take homological dimension, global dimension is as algebras. I don't know if it was Hipólito's question.
Yeah.
Okay, so it's as algebras.
Mm.
So, and this global dimension is the global dimension of the left modules, let's say, of.
Yes, for well, in fact, for Weil algebra, it's either on the left or on the right they coincide. But if not, you have to
Yeah.
You
we
need
are
to
in the
choose.
Noetherian case, supposing. So if we are in the Noetherian case, they coincide.
Right. And this is an algebra, so the Weil algebra in this case is infinite dimensional, right? So it doesn't.
Yes.
So Happel's theorem doesn't apply here, and
No.
right. And in general, the algebras that you're working with are infinite dimensional, aren't they?
For now, we didn't impose any question about dimension. So normally,
what's happening?
Yeah,
sorry.
you cannot see the whole slide, just a
Oh.
little.
Yes.
So
There we
this, yeah, because
No.
it's okay now.
Yes.
Yeah.
Yes.
Sorry.
Okay. So here is infinite dimensional. Many of the examples are infinite dimensional.
Right.
Yeah.
Yeah.
For a finite dimensional, well, yeah. No,
Yeah,
it's
so
okay.
it was already known for finite dimensional
Yes.
algebras by
Yeah.
Happel, as Claude stated. It was also
Yes.
known for graded connected
Yeah, graded and
algebras.
Hopf
I think that was
algebra.
Verger who proved it. You
Yeah.
even mentioned it.
Yeah.
Yes.
Okay, so one more classical case is finite
Yes.
dimensional.
Finite dimension. Okay.
Yeah.
Yeah.
Okay.
Yes.
So
This is
I
just
have
something to add here.
Yeah,
So,
exactly.
one more
I have a
question, right?
question.
Yeah.
Oh, sorry, please go on. I'll tell you.
And I think someone have a question for me.
Yes, I had a question about so here you're checking this condition on the global dimension of A, which is the same as geometric regularity, right? When you have a local, so in the commutative Noetherian case, having finite global dimension is the same as having a smooth.
Yeah, in the commutative case, it's the same.
And there are these conditions that generalize smoothness, both in the commutative and non-commutative case, right? So there's a Gorenstein condition, which says that, I can't remember if, yes, A has to have finite injective dimension and some further homological conditions.
Yes.
Have you considered some other theorems of this style applied to this
Well,
less
actually, for
smooth?
now, I didn't, yeah. I heard about it, but actually I didn't consider other similar style for this case.
Okay.
So I don't know. But yeah, but I think I have to look about it later. But yeah, but sorry, I didn't ever consider anything else more.
I'm asking because one thing we did with Andrea some
Mm-hmm.
years ago
Mm-hmm.
is, and so it's in different papers also with Laurent Rigal from Paris. What we did was to show that when the algebra is graded and connected, we gave an argument very similar to what you do to say, okay, it all depends on certain very specific properties of the trivial module. And you don't even have to check it in the category of all modules, but in the category of graded modules, which
Mm-hmm.
is kind of like the argument you give, right? This very big, very structural property actually can be reduced to checking a property of the trivial module on a very specific subcategory of modules, right? Not in the category of all modules, but on those that have an action, an H coaction and so on. So you sort of corner the problem very little, and then you say, okay, it's enough to check it here. We did the exact same thing, and it applied not just to smoothness, but also to these other homological properties. And we never pursued this, but I find it very natural that you can generalize this to
Yeah.
Hopf,
Okay.
so what is it? Algebras with coactions of Hopf algebras. So my guess is that a very similar argument to the one you gave should produce proves that, yeah, these properties are actually checkable just by looking at this very small module. And I was very surprised because I could really follow the argument you were giving, because we did a very similar thing in a much more restricted case. But you know, all these functors coming and going, the M tildes, and then transforming by modules into one-sided modules, all of that reminded me very much formally of that. So there's probably a relatively long-hanging fruit near this.
Okay.
Yeah.
Looking at those properties. Typical, more of a comment than a question comment.
Yeah, thank you so much. I will, yeah.
Do you have any other questions? It seems not. So thanks, Hoa, again for the talk and for accepting the invitation. And I don't know, I'm not in charge of the seminar anymore, so maybe Javi has to say what's next for the next week.
Yes.
I don't have that
Next week,
information.
which is the last week of this semester, we have Julie Simons.
Okay.
Okay.
Also the last of Najib friends.
Okay.
Of course,
Okay.
Hoa, you're
Okay.
invited to come next week too.
Yeah.
Yeah.
Okay, so
Bye-bye.
Yeah, thanks so
see
much.
you next
Bye-bye.
week.
Thank you.
Thank you.
Bye.
Bye.
Bye.